In this video, I'm going to go over the concepts and the questions for the section review on page 282. If we look at number 1, it asks, in which of the following situations should the objects be treated as a point mass, and then in which should the objects be treated as an extended object? Well, an extended object, if we look earlier in the chapter, it says an extended object is an object that has a definite, finite size and shape. That can be related to its path as well. So if we look at a baseball hit high in the center field, we don't always know its path. The different things could affect it and move it. So that we would look at as a point mass. We'd have to look at the entire thing. As it rotates, it may not change it as much. If we look at B, a baseball rolling towards third base, okay, now assuming the ground is level, that baseball will roll on a straight line, a continuous path. That is an extended object, where an A is a point mass. So look at C and D and see of those, which one is going to go on a continuous path and which one may not go exactly on a continuous path. If it goes on a straight path or a predictable path, that's an extended object. If it doesn't always move in a definite shape, that is a point mass. Number 2, the rotational analog of a force. Well, the force in a rotation is what we call torque, okay, and that's measured in newtons times meters, not just newtons. That's how it differs from a force. It's a newton meters, not just newtons, okay. And it's how something rotates and not just a direct force. On what quantities does it depend? Look at the equation. The equation is going to tell you what things you need to figure that out. When we go to number 3, remember tau for torque is force times distance times sine theta. Okay, that'll also help for the last part of number 2. So if we look at this, and I'm going to look at the force of the torque that is put with the 25 Newton force. So it says that it rotates through this point, and they call it O. And it says this force, 31 degrees here, 25.0 newtons. Okay, so let's put what we know. Let's put what we know into our equation. We want to find the torque of the 25 Newton force. So our force is 25.0 newtons. Our lever arm, it shows that this distance, 2.0 meters. It shows it in the picture. Now here's where we got to be careful. It says sine of theta, and it's always the sine of the angle between the force and the lever arm. That's this angle. Okay, so we need to do the sine of 59 degrees, not the sine of 31. 31 is the angle between the lever arm and perpendicular to it. So we need to use the 59 degrees. Okay, when we solve this out, two significant figures, because we have 2 there, we're going to get 42 Newton meters. All right, so that is one of the 3 on problem 3. The other two, they don't try to trick you on this step. Okay, that's why I picked this one. All right, so if we look now at number 4, how would the force needed to open a door change if you put the handle in the middle of the door? Well, that's kind of the same thing. If we put a force here compared to here, pushing on the door, rotating on its hinge, how would the force needed change? Okay, the middle of the door. So this is 2.0 meters. So we're out here doubling our distance. What would that do to the amount of force needed? And number 5, how does the length of the pedal arm on a penny farthing bicycle affect the amount of torque applied to the front wheel? Well, think about it this way. What would happen, the pedals on a bike, if the arm between where it rotates out to the pedal gets longer, how would that affect the torque of the bike if your lever arm got longer? Hopefully this helps. Watch this, get this assignment done, and get it turned in.